6.5, analyzing arguments and proof. A logical argument is made of premises and conclusions. Premises are statements that we accept for the sake of the argument. We just understand them to be true. It is not the purpose of logic to determine whether or not the premises are actually true. In logic, we suppose the premises to be true and then ask what statements follow using the laws of logic. The statements that follow are the conclusions. An argument is valid if the fact that all the premises are true forces the conclusion to be true. An argument that is not valid is invalid or a fallacy. So what we're going to try to do is prove if something is valid or not. The first concept is called Modus Ponens, or in other words, the law of detachment. It's a deductive argument form that states that if a premise is true and implies a conclusion, then the conclusion must also be true. It's also known as affirming the antecedent. I think all of that is kind of hard to understand, so let's just give you a kind of a bare bones example. That says if P, then Q. So you've got some kind of statement, and then you've got another statement. These would be the premises, and then you underline them to get to the conclusion. Think about it, something like this. If she eats potatoes, then she's the queen. And then the second line of that, she eats potatoes. So think about the conclusion we could make from that. If she eats potatoes, then she's the queen, and then we tell you that she eats potatoes, we can conclude that she's the queen. That form right there is called Modus Ponens. And like what you're going to do is you're going to use that to say, oh, this argument contains this form, therefore by Modus Ponens it's valid. That's one of the things that we'll have to remember. Or we can use a truth table. And this is kind of the long way. If we want to use a truth table, this would be the long way, like a brute force method of proving validity if you don't understand that Modus Ponens. But in order to use a truth table, we have to show that each of the premises implies the conclusion is a tautology. Now that means everything is true. Always true. So like the easy way where you don't have to think much is just going to be make a big, huge truth table, and if everything's true, it's valid. Okay? Determine whether the argument is valid or invalid. The argument says, if I win the lottery, then I'll buy a new house. I bought a new house. I won the lottery. Okay? So let's symbolize. If I win the lottery, then I'll buy a new house. I bought a new house. Therefore, I won the lottery. This is not the same thing as Modus Ponens. This is not the same thing. In order for this to be Modus Ponens, it would look something like this. Similar, but not the same. That's not what we have. This is not what we have. Like how it works, when they tell you that you've won the lottery, basically it works like I think of the game Chutes and Ladders. If you land on a certain spot, you get to use the slide, right? If you remember that game. But that's what happens. We landed on that spot L, so we get to move to the conclusion that H. That was Modus Ponens, but that's not what this says. We didn't land on the spot, so we don't get to use the slide. I'm guessing that this is going to be invalid. But how do we show that? The only way we know right now is to make that truth table. So here's what you have to do. We've got two components. So we should know by now how to set up a truth table. True, true, false, false. True, false, true, false. So what you do is you say, okay, premise 1 L implies H, and premise 2. Let's go ahead and put those inside brackets. Implies the conclusion. That would be your setup. So we do a truth table for that. L implies H. Let's shortcut this. L implies H. Remember that's true. True implies true is true. True implies false is false. That's the only time it's ever going to be false, a conditional statement like that. False implies true is true. False implies false is true. That's something you should remember from a previous lesson. So we're going to AND that with H. Let's go ahead and just copy H. H was true, false, true, false. So order of operations says let's do the AND there. True and true is true. False and false is false. True and true is true. True and false is false. And then we're going to do the conditional, but let's copy that L statement. L, true, true, false, false. So we're going to do this conditional. True implies true is true. False implies true is true. True implies false is false. False implies false is true. That's kind of our final column that we need to look at. And what we're trying to show is a tautology. Always true. Well, it's not always true. This is invalid. This argument is invalid. And more specifically, we can tell when it's invalid. It's invalid when L is false and H is true. If I don't win the lottery, but I do get a new house. What that's called right there is the fallacy of the converse. The fallacy of the converse remember converse, you switch them. It looks like modus ponens, so we want it to be modus ponens, but it's not modus ponens because of the converse of this conditional statement right here. Logical error that occurs when you assume that because the consequent of a conditional statement is true, the antecedent must also be true, essentially reversing the logic of the statement and drawing an invalid conclusion. All right, so when you see the fallacy of the converse, we're not talking about something that's a way to prove it valid. Modus ponens proves the thing's valid. Fallacy of the converse does not. Number 2, same question. Determine if this is valid or invalid. If I could be in 2 places at the same time, I'd come to your game. I did not come to your game. Therefore, I cannot be in 2 places at the same time. There's the symbology of that statement right there. Okay, so if we want to prove that, again, like the only way that we really know how to do this at this point is to make that table. So the table, I've got 2 components. There's our setup. Premise 1, P implies G, and premise 2, not G. I'm going to bracket those. Implies not P. So again, what we're looking for is everything true or what? So let's do this. Since I know that we know how to make a truth table, let's just fast forward to the end of the truth table. The very last step of the truth table would be when we get to here and we get, that would be our last step, okay? It'll be a good exercise for you to finish up that table if you want to, but that would be our last step. That is a tautology. Always true. Doesn't matter what happens with P and what happens with G, whether it's true or false. Everything's true. That statement, that logic is true. Therefore, this argument is valid. Okay? This has a specific name. This is called Modus Tollens, law of contraposition. All right? If P, then Q, not Q, therefore not P. That form right there is called Modus Tollens, and it's a way to show that an argument is valid. So the long way, if you don't understand what I'm talking about with Modus Ponens and Modus Tollens, the long way, you could always just make the table if you want. But if you understand this and if you recognize this and see this, it's faster. You're like, oh, that's Modus Tollens, that's valid. That's going to work. It is a deductive argument form that states if a conditional statement's consequent is false, then its antecedent must also be false. It's also known as denying the consequence. Then we've got another fallacy. Remember, the fallacy is talking about invalid. Fallacy of the inverse, a logical fallacy that occurs by assuming that if a conditional statement is true, then its inverse must also be true. In other words, if P then Q, if that's true, it does not follow that if, it does not follow that if not P, then not Q. That's not good. That's the fallacy of the inverse right there. So now we've got Modus Ponens, we got Modus Tollens. Those are ways to show that it's valid, but then we've got two fallacies, the fallacy of the inverse and the fallacy of the converse. Number 3, determine whether this argument is valid or invalid. I'll win this race or I'll eat my hat. I'll win this race or I'll eat my hat. I didn't win this race. I'll eat my hat. Now, this one, let's think through this. When we write these, we've got two premises and then a conclusion underneath. And it's understood that the two premises are true. So the first one says W or H, and then the second one says not H. Well, think about the or. Oh, I said not H, I meant not W. When this says not W, doesn't that mean that H is going to have to be true? In order for this to be true and this to be true, in order for both of these to be true, then H is going to have to be true. So this feels like it's going to be valid to me. Okay, and so how do we show that? Again, we can set up that table, W and H, and it would be W or H and not W, bracket, implies H. But let's save ourselves some time. Okay, we've already seen a bunch of these tables. That final column is going to end up being a tautology. This is valid. This argument is valid, which brings us to a third method for showing valid arguments called disjunctive syllogism. A logical argument that uses a disjunction or either or statement to draw a conclusion. And I think you can tell. You can look at this and say, well, okay, P or Q, not P, well, then Q has to be true. If we know that not P, not P, then it must be Q in order for that or statement to work. That's disjunctive syllogism. So that's your third method for showing valid. Okay. Number 4, determine whether this argument is valid or not. If you make your debt payments late, you will damage your credit record. If you damage your credit record, you will have difficulty getting a loan. Difficulty. Therefore, if you make your debt payments late, you will have difficulty getting a loan. So again, we're gonna show this with the table, right? That's kind of our fallback plan at this point. That's all we know. But think about it. Like, this might remind you of something from algebra class. If we land on this spot, think about the game Chutes and Ladders or some other game where you get to slide to a new spot. If you land on this spot, then you get to slide to this spot. But if you're on this spot, you would also get to slide to this spot. And so this feels right to me. It feels like the transitive property from algebra. If you land on this spot, then you get to slide past C to this spot. That feels valid to me. And it turns out it is going to be valid, but we've got L and we've got C and we've got D. And so notice that's going to be 8 rows, right? 2 to the third power. 2 to the third power. That's going to be 8 rows in our table, and we're going to go, oops. Oh no. And so we're going to build out this table, and we're going to have 8 rows, and we're going to do all of that work, and we're going to end up with a tautology. And if you can get to that, you know that that argument is valid. Which is your 4th method. Hypothetical syllogism, or reasoning by transitivity. There's your transitive property. A deductive argument that uses conditional statements, typically in the form if-then propositions. If P, then Q. If Q, then R. Therefore, if P, then R. It's just like the transitive property from algebra. If you land on P, then you get to slide all the way past Q straight to R. That makes sense, and this is the 4th one that's valid. So what do we have? We have Modus Ponens, Modus Tollens, Disjunctive Syllogism, and Hypothetical Syllogism. So, number 5, determine whether this argument is valid or invalid. All right, so if Ed reaches the semifinals, then Liz will be happy. If Liz is not happy, then Roxanne will bake her a cake. Excuse me. Roxanne did not bake her a cake. Therefore, Ed reaches the semifinals. Determine whether this argument is valid or invalid. Now, the long way is to make a truth table. ELR. There's going to be 8 rows in the truth table, right? But if you understand those 4 methods for showing things are valid, you could use some reasoning and reason this out. Okay, so let's look at this. I don't have this written very well on my board here, but or on my page here. this kind of looks like Modus Tollens. Remember Modus Tollens, if you go back and look, it said if P then Q, not Q, therefore not P. All right. So it's a little bit hard to see because when I gave you the definition, it was P's and Q's. Now it's L's and R's, but that says the same thing. I switched the negations around a little bit, but that's what that says. And so you can put some of that stuff together. Let's rewrite. Okay. So we've got these three premises. Okay. What I'm going to do is I'm going to use number 2 and number 3 with Modus Tollens to like conclude L. Look at how Modus Tollens operates. This, then this, but not this gives us not this. So I know it's backwards, but that's what that's going to do. We've got this, then this, but not that R. So what that would conclude is not L, which is L. So my statement 4, I'm using Modus Tollens and steps 2 and 3. Okay. But then if you look at 1 and 4, okay, 1 and 4, if you've got this and oops, you've got this, it would be nice if we had E. Oh no. It would be nice if we had E and we could slide to the conclusion. But this is backwards. This is one of those fallacies. The fallacy of the converse. The fallacy of the converse said P then Q, and if you have Q, you want it to be P, but that doesn't work. Okay, this isn't going to work. So we can kind of tell this is invalid. We've got these two pieces right here and right here form the fallacy of the converse. Now, I freely admit that's kind of hard to understand. If you got it, it's really fast. It's much faster than the truth table. But if you don't understand that, you can always go back and do the truth table. We know it's valid when they're all true. It's invalid when anything is false. But this one is invalid. So then the summary. We've got any one of these 4 things to use in combination with one another to show an argument is valid, or make a truth table. And so again, you've got kind of a quick way or a long way, and just use the quick way if you understand it, and if you don't, you got to do the long way. Number 6. In addition to writing children's classics such as Alice in Wonderland, author Lewis Carroll also wrote humorous logic puzzles in his book Symbolic Logic. In each logic puzzle, he presented several premises, leaving the reader to find valid any conclusions. One of his puzzles is given below. What is the valid conclusion? All right. So babies are illogical. Babies are illogical. It would probably make more sense to think of it as an if-then statement. If it's a baby, then it's illogical. Okay. Nobody is despised who can manage a crocodile. So again, it's probably easier if you say if can manage. I did not spell that right. Crocodile, then not despised. That means the same thing. Nobody is despised who can manage a crocodile. So if you switch it around and say, if you can manage a crocodile, then you're not despised. Nope. Same thing. So if you're a baby, then you're illogical. If you can manage a crocodile, then you're not despised. And then illogical persons are despised. If you're illogical, then you're despised. Those are the premises in these problems. So this author, this Lewis Carroll, he wrote this book and he gave these three premises and he said, well, what do you conclude from that? And so it was like a workbook or like a puzzle book or something. You had to try to figure something out. Let's number them. Look at 1 and 3. 1 and 3. 1 and 3, if you take together 1 and 3, think about it. If you hit B, then you slide to I, but if you're on I, then you can slide to D. That's that transitive one. To me, that's the easiest one to see, I think. Well, it's one of the easier ones to see. I can use 1 and 3 and say if B, then D, because I can slide completely past I. And so behind it, you want to write how you got that. So something like 1 and 3 and transitivity. Hypothetical Syllogism was the more complicated name. Okay. What else can we do? Something else we can do that I haven't mentioned before, well, in this lesson, but last lesson we did, was the contrapositive. Remember, it was the inverse and the converse and the contrapositive. So you've got some kind of statement, and you switch it, and you negate it, and you switch and negate it. That's supposed to be and. You switch it and negate it. The contrapositive, you switch it and negate it. So if I take statement 2, I can switch it and negate it, and it would say the same thing. If I switch this and negate it, it would be D implies not M. That's statement 2 using the contrapositive. So there's another layer of difficulty on these problems because we can use what we did from before. This is statement 5. And we're just kind of playing around here. We're kind of playing with this stuff. And that was definitely the hardest part. But look at 4 and 5 now. 4 and 5. If you take those together, you're like, well, if I hit B, then I can slide to D. But if I'm on D, then I can slide to not M. I can say if B, then not M, using 4 and 5 and that transitivity again. Think about what that says. if you're a baby, then you can't manage crocodiles. That's kind of a weird thing to say. Let's condense that. Let's make that easier to read in the English language. We might say babies can't manage crocodiles. Yeah, I know that's a weird thing to say, but it's a logic experiment. We're just kind of playing around. You know, they're supposed to be silly. Humorous logic puzzles is what they said right here, but they are silly. But it's interesting that we can use logic to make a conclusion here. Example 7. Determine whether the following argument is valid or invalid. If tomorrow is Friday and sunny, then it is a beach day. Tomorrow is Friday. Tomorrow is not a beach day. Therefore, tomorrow must not be sunny. Okay. As always, we could make a truth table if we want, but let's try it again without. The truth table, it would have been FSB, it would have been 2 to the third equals 8 rows. And you can do it. It doesn't take that much effort. It doesn't take that much thought. You can do that. Or let's see if we can use our properties. So look what we've got. Statement 1 says this. Statement 2, statement 3. Those are our premises. And we want to try to conclude tomorrow must not be sunny. All right. I'm going to start with statement 1. I'm going to take statement 1 and I'm going to flip it around. I'm going to do the contrapositive of statement 1. Contrapositive means switch it and negate it. Okay. So now, if you notice, we've got this statement 4, but we've also got not B as one of our premises. So we can plug it in right there, and we can use that statement 3 and that statement 4. And which one is that? Let's look back real quick. That's Modus Ponens. That's Modus Ponens when you can just land on that spot. So statement 5, you take 3 and 4 together and you can conclude not F and S. That's statement 3 and 4. Modus Ponens. Now, we're at statement 5, not F and S. What I want to do here is I want to think about distributing that negative. That's De Morgan's laws. De Morgan's lets me distribute that negation. Remember, when we distribute, we have to flip the symbol from an and to an or. So I take statement 5 and I use De Morgan's law. Now, if you notice, you can take that statement 6, but since we know F to be true here, And we can look at this and say this is not F. So that means this part would be false. I know it's kind of confusing here, but if we know F to be true, then not F would be not true, would be false. And what that means is this one must be true. That's one of my properties again. So we take that step 2 and step 6 together, and we can conclude not S, which is exactly what we wanted in the first place. That was step 2 and 6. And look back at the one that has an or in it. That was the disjunctive one, right? Disjunctive syllogism. So this is valid. Determine whether this is valid or not. Yeah, this is valid. And this is the proof. All of this stuff is how we can prove it to be valid. Or, of course, if you don't want to do that, you can still make that truth table. Number 8, same question. Determine whether or not this is valid. If your teeth are white, you use extreme bright toothpaste. If your teeth are white, you will be more attractive. Therefore, if you use extreme bright toothpaste, you will be more attractive. This kind of sort of almost looks like that transitive one, but it's not. And so this makes me think that it's invalid. And you're not going to be able to prove it the way we did number 7 with these properties. You can't really prove that it's invalid using the properties. That's not going to work. One thing that you could do is just try to figure out some example of when the premises are true, but the conclusion is false. You could try to do it that way, and you might be able to just think about a scenario. Well, if this one's true and this one's false, then the overall thing is false. But if you're confused, we might as well just make a table. That's probably just the easier way to do it anyway. So I'm going to go in this order: W, B, and A. It doesn't really matter what order you go in, but that's the order that I wrote them down in: white, bright, attractive. We set up our table with 8 rows. And that's what it's always going to look like with 8 rows. Now, we got to look at the premises. Imply the conclusion. So I'm gonna shortcut this a little bit. Let's go with if W then B. W implies B. That's true implies true is true. True implies true is true. True implies false is false. True implies false is false. Well, all of these, when it's false, implies anything is going to be true. So we got kind of out of order here, or misaligned, rather. So just be careful with your alignment. Let's do W implies A. True implies true is true. True implies false is false. True implies true is true. True implies false is false. And then again, when it starts with F, we know it's going to be true. False implies anything is true. Look like that. All right, so now I want to AND them together. True and true is true. True and false is false. False and true is false. False and false is false. True and true. True and true. True and true. True and true. Now let's do B implies A. True implies true is true. True implies false is false. False implies true is true. False implies false is true. True implies true is true. True implies false is false. False implies true. False implies, those are both true. And then finally, I just want to do this to see if my premises imply my conclusion. True implies true. False implies false. False implies true. False implies true. True implies true. True implies false. True implies true. True implies true. Okay. So what we're looking for, remember, is a tautology. And this is not a tautology because they're not all true. We can look at this and we can say, well, it's not always true, so this is not a tautology. But not only that, we know this argument is invalid because of that. But not only that, we know that it is false. It is false when this scenario holds true. So it's invalid. This is an invalid argument, specifically when W is false, B is true, and A is false. So this argument is invalid.